how you learn physics. You don't need to memorize anything. You just need to know how to do you just need to know the reasoning. I will not test you on how to spell Bernoulli, so don't worry. So this is Bernoulli's equation, which is the most abused equation in physics. You will see a bunch of textbooks or videos giving you this Bernoulli's equation and just use it in places that is not related to energy conservation. This comes from energy conservation. It is the conservation of energy for a fluid, and we express it with density because fluid it makes more sense to use density for fluid instead of just the energy of the entire fluid. So when we look at Bernoulli's equation, you will see that 1/2 rho v squared plus pressure plus rho gh is a constant, or rho gy. So now, when we compare the pressure here and the pressure here, their height is the same. They are equally high, right? But at this point, the velocity is bigger or smaller? Good. So the shape of the tube will force the water to convert some of its energy into kinetic energy, because it needs to increase kinetic energy to pass through the tube. The potential energy stays the same. So the only place it can take energy from is the internal energy, which is pressure. So you will see that when the water passes through this tube, you can measure the pressure by a tube on top of it. The higher this water is, the bigger the pressure. So when you run the water inside this tube, you will see the water level here is smaller because the pressure is smaller. The pressure is smaller because the tube converts the internal energy into kinetic energy. Okay? So you see, when energy is conserved and you speed up the speed of water, you need to take the energy from pressure. So sometimes when the speed is faster, pressure will be lower. But it only works for energy conservation. What people like to use, what people like to use is to say, here the air is flowing, so the pressure is smaller. That's why the ball will go up. Here the air is flowing, the pressure is smaller, so the ball will go down. That's how they abuse Bernoulli's equation. But wait a second. This comes from energy conservation. The reason that the pressure here is smaller because the pressure turns into the kinetic energy. Pressure will only decrease if the extra kinetic energy comes from energy conservation. Now, why is this air moving? Why is this air moving? The fan, the hairdryer. The reason that this air is faster is because the hairdryer input energy to the air. The work done by external non-conservative force is non-zero. The reason that the air here is faster is not because it turns its internal energy into kinetic energy. It just gets extra energy from the hair dryer. So that's why you cannot use Bernoulli's equation to explain this phenomenon. You can only use Bernoulli's equation when the increase of kinetic energy comes from energy conservation. When there is something that is obviously giving energy to this air does not have energy conservation, or the energy of this air is not conserved. It comes from the hairdryer, and that's why this speed of air is faster, and the pressure doesn't need to be lower than the air down here. Okay? And the reason that the ball will go up is due to momentum conservation. Kalman effect drag it down, giving the air downward momentum, so the ball will get upward momentum to get back. Okay? Any question? All right, so one last thing for since I already told you learn that pressure is actually the energy density of water. Surface tension is also a type of energy per watt density, but not volume density, but area density. So when you look at a water current, you learn that surface tension will have a force pulling this tube. So if you want to move this tube to the right, how big of a force do you need if the tension on top and bottom are both T? How big of a force do you need to push forward?
2T?
Good, 2T. Okay? Now, after you pull the curtain for a distance, you pull it for a distance, L, with just enough force. So the water current is not like moving now. You pull it really slow. You are using just enough force to pull the tube. And therefore, you are not increasing the kinetic energy of the tube. You are just pulling it really slowly. Initially, no water is moving, and at the end, still no water is moving. So the kinetic energy doesn't change. Does the external potential energy change? I'm pulling horizontally, so does the gravitational potential energy change? No, good. So, but I pull the stuff with force and a distance. I have done external work with non-conservative force, which is the force times this distance because it's in the same direction. So the dot product just becomes force times this distance. So they should equal to the increase of energy of the system. But the kinetic energy is not changing. The external energy is not changing. The internal kinetic energy is also not changing because they are not moving. So this must equal to the internal potential energy of the fluid. Where does this internal potential energy come from? When you look at the area of this surface, you see you increase the surface by Let's call this L, and this is D. The area up here is L times D, right? When you increase the surface, the amount of water at the surface increase. Those water will pull each other with surface tension. And therefore, the internal force can do work when you pull the two. Those work is the change of internal potential energy. So you know the work you done goes into the change of internal energy. And the work you done, this tension here, will be the surface tension times what? If the water curtain is wider, will the force you need be bigger or smaller? So you know it has something to do with this L. So what should you multiply here?
L.
Good. So the force you pull will be 2 times gamma times L. And the work you done will be 2 gamma L D, which is gamma times the change of area. You have LD up here, and you have LD down here. So the change of area is 2LD, okay? And that equals the change of internal energy. So you see, gamma times the change of area gives you the change of energy. So surface tension is actually the energy density per area. It is an energy per area, and if the water has more area, it has more energy. Okay? So, because we see that surface tension should be a energy per area, let's do a dimensional analysis. Surface tension is force per length, right? Surface tension times length